Hey, what we're going to be looking at now are compound inequalities. These are inequalities that have more than one part in them. You're either going to see the word and, the word or, you may see multiple inequality symbols in there. So our goal now is to start to look at what this means, how to solve them, and how to draw a graph for them. Now, what I have here is I have two terms on the outsides, one in the middle. I have two inequality symbols working on. So this is telling me that 4 is a bottom bracket, 8 is an upper bracket, and somewhere in the middle is a third region. So I'm looking for numbers that reside between 4 and 8. Now if I were to graph just this on the number line, just like I see it, this region right here represents x plus 2. It represents the numbers between 4 and 8. Another way to think of this is that I'm talking about the idea that 4 is less than x plus 2 and x plus 2 is less than or equal to 8. So I have these two ideas running at the same time. I have this idea, this limit down here, and this upper limit. Whenever I have this situation, I can break into two statements, the bottom and the top. Now the good news is, from here on out, I'm just going to be solving these two inequalities and then graphing them together. Now this one over here, I'm going to subtract 2 from both sides. So I end up at 2 is less than or equal to x. I'll be doing the same work on this guy, again, because I'm working with the same core. X is less than or equal to 6. Those would be my solutions. So if I want to write a solution out, I would write 2 is less than or equal to x, which is less than or equal to 6. That's my solution in terms of words. I can use any number as long as it's between 2 and 6. I could also write this as 2 is less than x, and x is less than or equal to 6. I can use this word and to split these. I'll write that out. 2 is less than or equal to x, and x is less than or equal to 6. Those are the same thing. And to be clear, let me add in one more thing here, which is that I subtracted 2 from both sides. I want to make sure I'm keeping track of my steps as I'm writing down my process behind my solution. The last thing I need to do now is come up with a graph of this. There are lots of different ways you can get to this graph. What I'm going to do is start with my number line. There's my number line. And I'm going to graph, I want to graph both of these inequalities separately and look to see if we're talking about an overlap, where they're both satisfied. So 2 less than or equal to x. Here's 2. Less than or equal to is a solid dot. Now, 2 less than or equal to x, if I were to flip it around so my variable is on the left, I write it like that, which means I'm going to be shading this way. If I graph this one, x is less than or equal to 6. Here's 6, solid dot. And I'm going to be going that way with it. Now, when I look at this, I can see the overlap, the intersection of these two terms. This region right here represents all the numbers that satisfy the first and the second statement. This number right here, number 3, makes this true, it's greater than 2. Makes this true, it's less than 6. Numbers over here make the first one true. Numbers over here make the second one true, numbers in here make both of them true. So my final answer as far as my, well, this should be filled in, as far as my compound inequality is concerned, is this region in the middle. When we see the word and, we're looking for an overlap. We're looking for things that have both qualities. So and is going to refer to where these two lines cross, that overlap. Let me try one more way to get to this idea of the word and in this context and see if this helps. I can talk about a group of students. So here's a group of students. We'll say those are the students who participate in football. And now there's another group of students who participate in marching band. If I want to talk about students who participate in both marching band and football, I'm talking about an overlap. I'm talking about an intersection of those two groups. So in this case, when I'm talking about inequalities, the word and has me looking for the overlap, where these two groups mesh. So all of these values make both of these two statements true. Let's take a look at another one of these. Let's take a moment and go back and talk about how these words and or work with inequalities and being graphed. Before we do a lot more algebra, let's get to some big ideas. For example, I've got x is less than 6 and x is greater than or equal to -1. Now I can write this as a single inequality because I'm using the word and. I've got this bottom barrier here that x must be bigger than -1. And I've got this upper barrier of 6. X must be less than 6. I can put those together and write it this way. X is going to be less than 6, and at the same time, greater than or equal to -1. So I'm taking this part over here, and then I've got this part right here. So those two statements are the same. This statement can be broken up into a statement using the word and. So now when I go to graph it, here's my number line, here's -1, here's 6. Now one way to think about this, since I wrote it in this style, I want x to be in the middle. If I think of it this way, I have the word and, so I'm looking for the overlap of these two inequalities. X greater than -1 is going that way. That's equal, greater than or equal to, so it's a solid dot. X is less than 6. Strictly less than, so it's an open circle. Going that way. When I look at where the overlap occurs, it's that region right there. So the graph of these two inequalities would be here. I've got numbers greater than 6, sorry, less than 6, boom. I've got numbers greater than or equal to -1, boom. So everything in here satisfies both conditions. Now when I introduce the word or, so here I've got x is greater than 5, or x is less than 2. First, I can't write these as a single compound inequality. I can't write them like this. It's just not going to work. Second, I'm not looking for where the intersection is. We call this the union, meaning we want things that make one or the other to be true. We've got two groups, we're going to put them together, and anything that's in either group counts. So it's that combination of the two groups as opposed to its intersection. Let's talk about that sports analogy again with our players. I've got football players, I've got marching band. If I want to talk about all the people who are in football or marching band, then everything up here in those circles counts. Because Everyone is in one or the other. And had me focus strictly on that overlap, because that's what and is interested in. But the word or allows me to have the two groups, anybody in either group. So, when I go to graph this, x is greater than 5. Well, here's 5, strictly greater than, so it's an open circle, and I'm going off this way. Here's my 2, strictly less than, so it's open circle, and I'm going off this way. And there you go. This would be the graph to go with this. All of that, make it true. All of that, make it true. What doesn't work are numbers here in the middle, like the number 4. 4 doesn't make this true because 4 is not greater than 5. 4 doesn't make this true because 4 is not less than 2. Numbers like 0 make this one true, so the overall statement is true. Numbers up here like 6 make this true, so the overall statement is true. For an or statement to be true, I need to have one or the other. Again, I hold up a student and say, this student's in football. Well, then he is in football or marching band. Hold up another student and say, this student is in football and marching band. That's okay, because it makes one or the other part true. The only time I would have a false statement, statements that are not part of my solution, is when I bring up somebody who's involved in neither. Let's take a look at another algebraic example that's going to use these compound inequalities as part of our solution and the graph.